Okay. All right, so we're going to be doing the valence bond theory and molecular orbital theory. This is where we start really kind of moving into new materials, but still related to old stuff, okay? So, Lewis structures, these can't account for a number of different things we've already started seeing, and we will see in the future, okay? And so, for example, electron delocalization. In a Lewis structure, we don't really have the concept that electrons cannot be localized. Now, what does localized electrons mean? Localized electrons have atoms on each end, okay? So if you have a desk between two people, can it move around a lot? No, you've trapped it in place, right? Because the two people are holding it. What if you have a desk that you're only holding with one hand? Can it move around a lot? Yeah, you can. If something tries to grab this marker from me, they're grabbing it, right? And we're sharing that marker or they're fully losing it. Okay. So if I have something that is not directly between those two atoms, they're going to be delocalized electrons. Okay. All right. Now, Vesper theory cannot predict a molecule's extended geometry. It does not indicate the relative positions of atoms separated by more than one atom. It may predict the trigonal planar geometry of each C in the ethene, which we're seeing right over here, but does not inherently predict our lack of rotation. And so we get a real problem here. Ethene cannot rotate. This does not exist, where we have it like this, and these hydrogens are in different planes. That doesn't exist. It's not possible. Okay? According to Vesper, it seems like it's possible, doesn't it? But what happens is we need to understand what these molecular orbitals actually look like. Once we understand that, we quickly realize, no, it's not possible at all. These hydrogens just cannot rotate at all. They are stuck. That's a planar structure. They can't rotate in any way whatsoever. Okay? All right, so this is valence bond theory. This is going to describe where electrons reside, both before and after bond formation. You've actually started this back in General Chemistry 1, talking about this, but you probably forgot a lot of it because it doesn't really get used a lot in Gen Chem 2. And then it was sort of half useful, and so you probably just like shunt. Goodbye. So a covalent bond has that form. Well, what a covalent bond is you have two half-filled valence orbitals, right? Then they're going to overlap in space. They will then share those electrons with those overlapping orbitals. They'll mix those orbitals together, and that's going to build up that region between the two atoms. The new orbital is then going to accommodate the bonding electrons. It's going to allow them to be shared between the two atoms. Okay? So think of it a bit like this. When you put your hand to shake a hand, how do you cup it? Everybody do it with the partner next to you. Get ready to shake hands. Get your hand ready. You have an absence of space, don't you? So you have a half-filled space, just like a half-filled orbital. When you shake the hand, go shake it. Shake it. Okay, what did you do? Yeah, you made two bonds. You're the central atom there. We got a propane there, we got a butane there, we got an ethane, and then methane right there. And so you're actually doing essentially the same thing as a bonding, aren't you? So you have a partially vacated space that hand could be in, and you overlap those vacated spaces so that you fill in the gap between, right? And this allows you both to hold on and pull on the objects within that space, right? Which is your hands. Okay? That's bond. Okay? Okay, so these are the orbitals. You may all recognize those orbitals, hopefully. Okay, when I'm looking at these orbitals, what does that actually tell me? Exactly, yes. It's the location you have a 90% chance of finding those electrons. Okay? Whenever you see these hard shell ones that don't fade off, it's 90%. Okay? This one being the s orbital, that being that first block on the periodic table, right? This being the p orbitals. See how they have directionality to them? Okay? So these p orbitals, when we're looking at those, they have an x, y, and z, don't they? Okay? Each of those can have 2 electrons in them. And they each point in different directions in space. Okay? Note, these are both representations of p orbitals. Those are probably more accurate when you're actually looking like a lone pair or something. Okay? Once you actually have something on the other side, they lengthen out like this a bit more. Okay? Because it's going to contain the electrons between them, right? But in your head, this is probably a better like way of thinking of them in your head. Okay? They're not actually like a figure eight. They're more like that. They're like a figure eight with a tire. All right. And I'm not going to cover the d orbitals right now, but you've probably seen the d orbitals somewhere or another. We mostly will ignore d orbitals in this class just because everything's carbon. But so right here, this is 2 hydrogen atoms overlapping. It's going to be a direct overlap between. And so when they overlap, what's going to happen is, remember, they're overlapping the space the electrons are going to be in, right? So when they actually overlap, that little divot here is going to get filled in because it's not energetically less favorable to be there than it is right there. Okay? That just is no longer true because we have positive charges on both sides, right? So it tends to fill that space in. Okay? Notice, however, this part has some of it reduced. Okay? This is actually literally going to be the combination of these 2 orbitals combining together to form that. Okay? Now, can matter or space be created or destroyed? Not at all, right? And so right here, we had 2 orbitals going in. How many orbitals do we have coming out? I only showed you 1, but how many do we actually have? 2. We have to have the same number coming out. Okay, this right here is a sigma bond. That's a direct overlap. Every time I hear sigma bond, what am I going to think? Direct overlap, right? It doesn't actually mean s orbital overlap. You can make sigma bonds with p orbitals. Okay? All single bonds automatically have to be sigma bonds because they're direct overlaps. That's how you get a single bond. Okay? Literally, it's the most energetically favorable to directly overlap, pull things together. There you go. Okay, I am a little over time. There we go. We'll start in here next time. You all have a wonderful day. Are there any questions, concerns, comments, tap dance routines, party tricks? No? Feats of incredible athletic ability? I'm sorry? I'll give you So I may not give you every single one. So if you ever have I may not give you every single one. I will give you some formula. But overall, if you want to make sure you have a specific formula, because I tend to give you like.
So I went to the Cumberland bookstore and the Shinecourt textbook was like available for purchase.
Okay.
I don't know if you don't know anything about that.
They're supposed to be trying to fix it.
Okay.
So what happened is,
Because it says that like I can only use my financial aid by like September 13th, 14th.